Stanford University.
Going way beyond the material of the course, but let's just talk about it for a minute. The model we talked about had a Hamiltonian, or an energy, which is just C times P. P can be positive or negative. The wave functions for a given P are just e to the IPX. And there's nothing better about e to the plus IPX or P being positive or negative. They're both perfectly acceptable plane waves, but one of them has positive energy and one of them has negative energy. Just reading off here. Now, negative energy is not such a good thing in the real world. Negative energy is not such a good thing in the real world because if there were particles of negative energy, the world would be unstable. The vacuum would not be, an empty space would not be the state of lowest energy. You could take empty space, which we can say has zero energy, and then just start putting in particles of negative energy. Particles of negative energy will lower the energy, and anything that lowers the energy tends to be favored. You can make lots and lots, more and more particles of more and more negative energy. You have to get some positive energy from someplace. You have to get some positive energy from someplace, but you could, for example, radiate photons and at the same time produce more and more of these negative energy particles. If there were particles of negative energy, the empty space would just be unstable, unstable with respect to creating more and more positive and negative energy particles. You have to conserve energy, so you have to do both, but that would happen. If there's only positive energy particles, by contrast, there's no way that energy conservation will allow you to make them. If there are only positive energy particles and the vacuum has zero energy, it's the lowest energy state and nothing can happen to it to create particles. So a good stable world requires all particles to have positive energy relative to the vacuum. This is not a good stable world. Okay, so what do you do about it? Well, it was Dirac who understood what to do about it, but only in the case of fermions. Now, what are fermions? Fermions are simply particles that cannot be in the same state. Two of them cannot be in the same state. That's a rule. Where that rule came from, it comes from relativistic quantum field theory, but it's the same as the Pauli exclusion principle. If you know a little bit of chemistry, you know that two electrons in an atom can't be in the same state. And you have to fill the atom with particles of different energies, different states. And the same is generally true. Particles that are not, that participate in the Pauli exclusion principle are called fermions. Why they're called fermions, I don't know. I mean, they should be called Paulions. It's obvious they should be called Paulions. And particles which don't participate in a exclusion principle are called bosons. But of course, properly, they should be called Einsteinons, but it was Einstein who first studied them. Never mind. Fermions and bosons. Fermions can't be put in the same state. Bosons can't. So what Dirac said was, look, I have a very simple solution to all of this. Just imagine that the vacuum, empty space, is really a state in which all the particles of negative energy are present simultaneously, filling up the vacuum. You simply can't put any more in because you're not allowed to put particles into the same state, but everything else is empty. In fact, if you were to say, think about it for a moment, let's assume that the real vacuum is the state of absolute lowest energy. Absolute lowest energy. Now take absolute empty space, what you think of as ordinarily empty space. Is that the state of lowest energy? No, I can put one particle of negative energy in, lower the energy. So there's a state of lower energy. whatever state you say, I will find another negative energy particle to put into it and lower its energy. The only way to have the state of absolute lowest energy is to simply fill it full of all the particles which have negative energy. In other words, all the particles with negative momentum. Sounds crazy, but it turned out to be right. But you can only do that with particles which have the property that you can't put more than one of them into the same state. If you could put more than one of them into the same state, there would be no end to your ability to keep dumping negative energy particles into the vacuum. All right, so this is a reasonable theory. It's a Dirac theory. It's a very simple, basic, baby version of the Dirac equation is what it is. And it's an okay theory for neutrinos, or for one-dimensional neutrinos. It is not a good theory for photons. Photons are bosons, and you simply can't play the same game. If there were negative energy bosons, you could simply dump them into the same state, more and more and more of them, and simply destabilize the world. So no, this is not a good theory of bosons. It's a good theory of fermions. But that's taking us way beyond this course, this quarter's material. We've covered, in a sense, a lot about the foundations of quantum mechanics and very simple quantum mechanical systems. We've covered almost nothing about what we could call the applications of quantum mechanics, so not even the applications of quantum mechanics, but studying quantum mechanical systems. We didn't even get to the harmonic oscillator. That's a disgrace. But we're not finished with quantum mechanics. Next quarter, we're going to do relativity and field theory, but then we're going to have to come back to quantum mechanics in order to study more about the basic structures that appear in quantum mechanics. So it's sort of embarrassing to teach a whole course in quantum mechanics and never get to the harmonic oscillator, but that's where we are. So you can ask for your money back, I don't know. On the other hand, it does seem people had a lot of fun with the ideas of entanglement. I didn't expect such a response, particularly this, and some of it was extremely interesting and well done. Some of the chatter back and forth on the internet, I actually did follow it, and sometimes it was generally good and sometimes excellent. So I got some sense of satisfaction out of teaching that. We're going to go on a little bit today about the Schrodinger equation. Not the general Schrodinger equation, but the special Schrodinger equation that Schrodinger actually wrote down. The connection with the things we've learned up till now is through the wave function. And the wave function is simply the amplitude that a particle is located at a particular position. In other words, it's the inner product of whatever the state vector happens to be with a state of definite position. And we can also write a momentum space wave function. The momentum space wave function is just the projection of the same state, whatever it happens to be, onto a momentum eigenstate, eigenvector. The momentum eigenvectors and the position eigenvectors, or rather the momentum wave function and the position wave function are related, and they're related by Fourier transform. That's the basic structure of position and momentum. If a particle has more than one direction to move in, for example, let's suppose it can move in the xy plane, then you characterize the position of a particle by two coordinates. The two coordinates commute. You can measure both the x and y position of a particle simultaneously. Now, is that something that follows automatically from what we've said up till now? No, not at all. It's really an empirical fact. It's an empirical fact that the structure of the quantum mechanics of particles only conforms to experiment if we assume that the different coordinates, the different directions that a particle can move in commute. And that means that the wave function is really a function not of a single variable, but a function of a collection of variables, the collection of variables being the position, the various coordinates of the particle. If we have several particles, then the wave function becomes a function of the coordinates of all the particles. We're not going to go into that today, but I just tell you that the wave function thought of, the wave function of a collection of particles, is not a function of three-dimensional space. It's a function of all of the coordinates of all of the particles. In the same way that phase space, the phase space of a particle, is described by a collection of a large number of coordinates and momenta in the case of classical physics, the wave function of a particle is a collection of a system, is a collection of, a function of the collection of all of the coordinates. So for example, if you have 10 to the 23rd particles, psi would be a function of 10 to the 23rd coordinates. Okay, so that's the basic structure. And you can go to momentum space by Fourier transform and write the wave function instead as a wave function of all of the momenta of all the particles. You can even have mixed situations, mixed representations, where you may describe a wave function in terms of the coordinates of some of the particles and momenta of the other particles. This is also allowed. But we're going to focus on the case of one-dimensional motion again. We're going to come back to that and just discuss the behavior of the wave function, its properties, just a little bit. Mainly properties of the Schrodinger equation. First, the uncertainty principle. Okay. Where does the uncertainty principle come from? It comes from the fact that x, the coordinate, and p don't commute. Whenever two coordinates or two observables don't commute, it becomes impossible to measure both of them simultaneously because there aren't eigenvectors which are eigenvectors of both observables. In particular, the eigenvectors of x are extremely different. Every eigenvector of x is extremely different from every eigenvector of p. The eigenvectors of x are sharp, narrow, highly localized functions in space. And the eigenvectors of momentum are, first of all, complex, e to the I px, but their real and imaginary parts are oscillations over all of space. And so they're sort of space-filling. They're not space-filling. It's not that the particle fills space. It's just that the particle is everywhere equally likely to be everywhere when its momentum is known. So that's the most primitive observation about the uncertainty principle. If you know the position of a particle, you certainly don't know its momentum, or if a particle is in a position eigenstate, it's very far from a momentum eigenstate. If it's a momentum eigenstate, it's very far from a position eigenstate. That's the most primitive version of it. We could say more qualitatively. And then we'll come to quantitative. We'll come to quantitative precise theorem in a moment. But if we look at the wave function as a function of x and its relationship by Fourier transform dp over the square root of 2 pi psi twiddle of p e to the I px. And I won't bother writing the other relationship. The other relationship is the one that writes psi of p in terms of psi of x. And just start fooling around trying to construct psi of p or psi of x one from the other by Fourier transform, you very quickly discover that the narrower the distribution in X, the broader the distribution in P will be. That's a property just of the Fourier analysis, that the narrower psi of X is, the broader psi of P is, and vice versa. If psi of P is very narrow, it means that it's basically a single plane wave, then it's very broad in X. And so that's a pattern of Fourier transform. The narrower a function is, the broader its Fourier transform is. That's the qualitative understanding of the uncertainty principle, but let's try to do a little bit better. Let's try to see if we can define the notion of uncertainty and then see if we can prove a theorem. Okay. I'm going to prove a slightly simplified version of the theorem, mostly because there's just too much on the blackboard if I prove the full general theorem. I'll prove a simplified version of it, but the simplified version of it contains the basic ingredients. All right, first of all, what is meant by the uncertainty in a variable? You have some distribution for that variable, and the first thing to do before discussing the uncertainty in it is shift the axes so that the average of X, let's say this is X, so that the average of X is 0. You can always do that. Whoops. If the average of X is not 0, let's suppose you have some wave function like that. X equals 0 is over here. If you put your center of coordinates over here, obviously the average of X, the expectation value of X, will be negative. If you put your coordinates over here, the average of X will clearly be positive. And as you move the origin, you'll eventually find a position where the average of X is exactly equal to 0. So let's simplify our story by shifting coordinates. This is just a shift of coordinates, just shifting our coordinates until the average value of X is equal to 0. Okay, so average of X is equal to 0 first. Then what? Now, we've done it. Average of X is equal to 0. What is the uncertainty? The uncertainty, by definition, is the average of X squared. Okay? And looking at the average of X, it's 0 because anything on this side is balanced by something on this side. X is positive over here, X is negative over here, so looking at the average of it, the average will cancel if you choose your axes in the right place. But the average of X squared measured relative to this located axis here, will not be 0. X squared is not 0 here, X squared is not 0 here. In fact, X squared, the only place where X squared is 0 is right at the origin. And so there's no way that the average of X squared can be 0. And in fact, the broader the wave function, the larger the expectation value of X squared will be. Right? That's clear. So a good measure of the width of the distribution, you can call it the uncertainty in X, and it is the definition really of the uncertainty in X, is the average of X squared. The average value of X squared with a given probability distribution, given that the average of X itself is equal to 0, that is the uncertainty in X. And it's just called delta X squared. It's just called, it's a positive number, delta X squared, and the broader the distribution, the larger it will be. All right? How do you calculate it if you know the wave function? Very simply. You take the integral of psi star psi of x, that's the probability to find the particle at x, times x squared. That's the expectation value of x squared. Okay? That's the average of x squared. Probability to find the particle at position x times x squared. That's the definition of the square of the uncertainty. That's the square of the uncertainty of x. And as I say, it's definition, but it's a good definition. Let me rewrite it up here. Delta x, and I'll square it, is equal to the integral of psi star psi times x squared dx. All right, now what about the uncertainty in momentum? The uncertainty in momentum is defined in a very similar way. One other point. This is equal to psi x squared psi. It's the expectation value in the state psi of x squared. Okay. Thought of as a quantum mechanical, this is a quantum mechanical formula, the expectation value of x squared. That's the uncertainty. What about the uncertainty in momentum? In fact, for that matter, what about the uncertainty in anything? The uncertainty in anything, assuming its average is equal to 0, is just the average of the square of that quantity. That's a general definition. Incidentally, if you don't want to shift the coordinates so that the average is equal to 0, you can use another definition. And the other definition is that it's the expectation value of x squared minus the expectation value of x squared. These are two different things. The expectation value of the square of something is not the square of the expectation value. In particular, if the expectation value of x is equal to 0, it does not follow that the expectation value of x squared is equal to 0. This is a more general definition of the square of the uncertainty in x. But as I said, you can always shift your axes around so that this is equal to 0 and just choose this one here. Okay, what about the expectation? What about the uncertainty of momentum? The uncertainty of momentum is defined in essentially the same way. You can define it, if you like, using the Fourier transformed wave function, and then it would just be, I'm not going to use this definition, but let's just do it. Delta p squared would be the integral psi twiddle of p, psi of p, times p squared dp. This would be the probability that the particle has momentum p times p squared integrated over p. But I'm not going to do it this way. What I'm going to do is just observe that this quantity over here is nothing but psi p squared psi. And now I'm going to work in the position representation. We can do that because we know what the operator p is when it acts on a wave function psi of x. What does p do? What does the operator p do when it acts on a wave function in the x basis? What it does, well, first of all, whenever you take expectation values or inner products, you have an integral dx to do. All right? From the bra vector here, you have psi star of x. The ket side of this is p squared times psi. And what is p squared? P is minus I d by dx. I'm using now that the momentum operator p is minus I d by dx, and p squared is just minus d second by dx squared. Second derivative, that's what p squared is. You act twice with p, once and then twice. So This is equal to the integral dx psi star of x d second psi by dx squared with a minus sign. The minus sign coming from minus I times minus I. Okay. Now you look at this and you worry a little bit. There's a minus sign here. How can the uncertainty in P be negative? What does it mean to have a negative uncertainty in P? There's a minus sign here. What's going on? What's going on is that the integral in here is negative. That's all that's going on. The integral is here. And how do you see that the integral is negative? You integrate by parts. So I'll just remind you the rule for integrating by parts is if you have, we're going to use this over and over. If we have two functions, f and g, then the integral f dg by dx is equal to minus the integral df by dx times g dx. This is true as long as f and g go to 0 appropriately at infinity, so that the boundary terms don't contribute in the integration by parts. All right, but just look at the structure of it, because we'll use it over and over. You can switch the derivative from one factor to the other factor at the cost of a minus sign. All right, that's the basic rule. Okay, so this is the second derivative. The second derivative is also, of course, a first derivative. Namely, it's the first derivative of the first derivative, d psi by dx. Let's do an integration by parts. All we have to do is switch the d by dx to psi star and change the minus sign. Okay, so this becomes dx. Let's put the dx over here. The d by dx can switch to the psi star at the cost of a change in sign. So this becomes plus, and this becomes d psi star by dx. Now look what we have here. We have d psi by dx, and we have d psi star by dx. This factor is the complex conjugate of this factor. They're just complex conjugates of each other. And what happens if you multiply a complex conjugate, a function by its complex conjugate? First of all, it's real, and second of all, it's positive. So the integrand in here is positive. The sign got changed to plus, and this is most definitely a positive integral here. So p squared, this is the expectation value of p squared. Okay.
Do we know that the average of p is 0?
We can always shift p until it is 0. Now, the real question is, can you have both the average of x and the average of p equal to 0? That's not so obvious. The answer is yes. You can always shift. First, you shift to x equals 0, and then you can shift to p equals 0. There's a trick. You know, I think let's come back to it. Ask me again. I don't want to get off the track. The answer is yes. You can take a wave function and shift it both in x and in p until both of them have average equal to 0. We'll come back to it. I'll explain to you why in a little while. But let's suppose we've done that. Okay? And let's see if we can find a relationship between the uncertainty in x and the uncertainty in p. Not a relationship. Well, I suppose it's called a relationship in mathematics, but an inequality is what I want. An inequality. The inequality should be such that when delta x is small, delta p is big. When delta p is small, delta x is big. Or better yet, that the product of delta x times delta p cannot be smaller than what? Than h bar. Now, I've lost h bar in here. I've lost h bar because I've set it equal to 1. We'll put it back later, but if you want to put it in here now, we should probably put it in here as a 1 over h bar squared here. An h bar squared here and an h bar squared here, but let's not, do I have it in the right place? Yes, I do. But let's work with h bar equal 1, and later on when we're finished, I'll put back the dimensional quantities. Okay, so here we are. What tools do we have to construct inequalities? There's basically there's a zillion inequalities in mathematics, but probably the most famous, the most useful, and the only one that I know that's particularly useful is the triangle inequality. Everybody know the triangle inequality? Some people do, some people don't, so I will tell it to you. And it comes in two forms. It's a statement about triangles, of all things. What it says is if you have a triangle, that the sum of any two sides is bigger than the third side. Obviously true, right? The sum of this side and this side. Why is that? Because the shortest distance between any 2 points is a straight line. So the shortest distance between these 2 points is this one, and the other two sides, the sum of the other two sides is certainly bigger. So if we have 3 sides, that's a statement. There's also another version of it. I'll tell you what, I think I'll prove it. I'll prove the other version, but you know the other version very well also. Let's call this one A, let's call this one B, and let's call this one C. Okay, so A plus B is bigger than C. Or A plus B is bigger than C, bigger than the size of C. Okay, A plus B is also, by the same argument, I mean, it is the same thing, is bigger than A plus B. If these are vectors, think of these as vectors. Here's a vector A, here's a vector, well, let's put it this way. C is not A plus B, is it? It's A minus B in this case, right? I think I want to think of it this way. A, B, C. Okay, it's still a triangle. A plus B is bigger than C, which is the same as saying it's bigger than A plus B. Let's square it. Let's square it. Then this becomes A squared, square of the side of A, plus B squared, plus twice AB is bigger than this guy over here. But what's the square of A plus B? It is A squared plus B squared plus twice the dot product of AB. Where did I get that from? I wrote that A plus B squared is just A plus B dot A plus B. That's the square of the length of a vector, and that's A squared plus B squared plus twice the dot product of A and B. And so we have now an inequality from which we can erase A squared and B squared from both sides. Here's another form of the triangle inequality. Let's erase the 2's. And what it says is if you have any two vectors, given any two vectors, here's one vector, here's another one, AB, that the product of the length of one of them times the length of the other is always bigger, I think this 2 disappeared, is bigger than the dot product. Okay. There's another way to think about that. What is the dot product in terms of the length of A and the length of B and something else? What else do you need to know to calculate the dot product? Cosine of the angle. So A dot B is, of course, nothing but A B cosine of the angle. And cosine of an angle is always less than 1. So the triangle inequality is pretty trivial. It simply says that the magnitude, the product of the magnitude of two vectors is always bigger than the dot product between them because the dot product always has a cosine in there. Now this is true for vectors in 2 dimensions, 3 dimensions, 100 zillion dimensions. It's even true for vectors in complex vector spaces. It's just generally true for vectors in any kind of vector space that the magnitude defined as the square root of the inner product of the vector with itself, that this inequality is true. In fact, let's just write it as A dot B. And let's square it because we're going to use it in the squared form. A squared B squared is greater than A dot B squared. I just squared, I haven't done anything very significant. And that's the inequality that we're going to use.
It should be greater than or equal to.
Yes, it should be greater than or equal to. The only time it's equal is when A and B are in the same direction. Right, that's right, greater than or equal to. When cosine theta is equal to 1. All right, that's going to be our trick. So I don't think I need this anymore. We'll come back to it. Yeah, well, we will. Kind of looks promising. We have a delta x squared here, sort of like a squared. We have a delta p squared here, sort of like b squared. And we want to show that it's bigger than something. All right, so the trick is to define the right a's and b's in terms of size and x's and so forth, and then just use the theorem. But I'm going to make one simplifying assumption. I've already made 2 simplifying assumptions that the expectation value of x and p are 0. That I will show you how to arrange, and there's no trick there. The simplifying assumption I'm going to make, only because I don't want to fill up the blackboard with more algebra than I need, than necessary. This is something you can sit down with at home and go through it for the more general case. I'm going to assume that the wave function psi of x is real. If I didn't, we'd be chasing around psi's and psi stars, and I would eventually tire you out, and you would probably lose the thread of the argument. So I'm going to assume that psi is real. It'll save us some algebra. It's not general, but it's very easy to fill in the steps for complex psi. Easy, but it takes a few more lines. And I just after sitting down and doing it on a piece of paper, I just decided it was too much for a blackboard presentation to do. Better to do it for the simple case. So psi is real. Okay, so here we are. We can get rid of the psi stars then. And I think I lost an equation here. Using the fact that p is minus I d by dx, we proved that this is equal to integral d psi star by dx, d psi by dx. Just quickly to remind you how we did it. P squared was a second derivative, well, minus a second derivative, and then we did an integration by parts to take one of the derivatives and put it over here. Okay, so that's delta p squared. And what we're going to try to prove is that the product of this times this is bigger than something. Product of this times this is bigger than something. Okay, and to do so, it's just a trick. Now think of A and B as vectors. In fact, you can think of A and B as either bra vectors or ket vectors. Since psi is real, it doesn't matter whether they're bra vectors or ket vectors, but here's what it's going to be. The one vector A, I'm writing them now in bra ket notation. the triangle inequality is perfectly true for bras and kets as well as for ordinary vectors. All right, so the vector A is going to be described as going to be the vector whose wave function is not psi of x, but x psi of x. A is the vector whose wave function is x psi of x. In other words, it's x operating on psi. And B is going to be the vector p times psi, or basically minus I d psi by dx. When I write equals here, I mean to say that A is the vector whose wave function is psi of x, B is the vector whose wave function is d psi by dx. And we're going to apply the triangle inequality to that. Okay. Notice that with this definition here, delta x squared is a squared. Look at it. The inner product of A with itself, a squared, is just the integral of psi star psi times x squared. So this is here a squared with this notation. What about this one? This one here is essentially b squared. It's the inner product of b with itself. How come I don't have I have a minus I d by dx here. If I put minus I d by dx over here, I would have minus I times minus I, which is minus 1. How come I don't get how come I have a plus 1 instead of a minus 1? Complex conjugation. Yeah, so this is b squared. That's a squared. And a squared times b squared is this. All right. It is also delta x squared times delta p squared. So delta x squared, delta p squared, a squared, b squared. The triangle inequality is literally talking about delta x squared, delta p squared. So now let's look at the other side of the inequality here. The other side of the inequality is a dot b squared. So let's compute a dot b. It's the inner product of these two vectors. Right? And then we square it. Then we take its absolute value and square it. Because we take its absolute value, I don't have to keep track of i's, minus signs. In the end, they'll all go away because I take the absolute value. And so the inner product of a dot b is going to be equal, it's going to have an integral. Oh, one thing. I did say that I'm going to choose psi to be real. So all of these psi stars don't matter. They're just psi. Every place you see psi star, you can think of psi. Okay, so let's take a dot b squared. That's going to be a, which is psi of x, x. I've just written this in the opposite order. And then times b, which is going to be d psi by dx. As I said, I'm not worried about signs or i's for the simple reason that in the end I'm going to take the absolute value of this. So that doesn't play any, that will play no role. And let's look at this quantity. Now, we have a dot b squared, so I can multiply this by itself. If I wanted to multiply itself by itself, I could multiply it by another integral of the same type, y d psi by dy. This is dx. This is dy. But all I'm doing is writing the same thing twice. So if I can evaluate this, I am also evaluating this. Okay, so here's the trick. The trick is to say d psi by dx times psi. Does that ring a bell to you? D psi by dx times psi?
The derivative log, right?
No. No, not the derivative of the log. It would be the derivative of the log if it was in the denominator. You're on the right track, though. It's the derivative of the square of psi. It's 1/2 the derivative of the square of psi. the derivative of the square of psi is equal to twice psi d psi by dx. So apart from a factor of 2, what we have here is x times the derivative of psi squared with respect to x. Everybody see that? Yell out if you don't. Okay. So I can remove this psi here and replace this by psi squared. And at the same time, put a factor of 2 1/2 somewhere. I do the same thing with the other factor. Same thing here. Psi squared. Why, another factor of 2, which makes this altogether a factor of 1/4. And as I said, this is just a, I don't even know why I'm doing it. I should just write square. But I just wrote the square by writing the same thing down again. Okay. Next, integration by parts. You have a derivative here. It's a derivative of psi squared, but it's still just a derivative. And when you have a function times a derivative to be integrated, you can switch the derivative to the other function at the cost of a sign. But really, there's no cost in sign because there's another sign from this one over here. All right, so there's no real cost in sign, and besides, we're taking the absolute value. So this is equal to integral of psi squared times dx by dx. And likewise over here, integral psi squared dy by dy. Dx by dx, that's familiar. That's just 1. And this is just squaring the same thing again. We are finished. We're finished because what is this integral of 1/4? Well, forget the quarter. What's the integral of psi squared? The psi squared is psi star psi. If psi is real, psi star psi is the same as psi squared. What's the integral of psi squared? 1. 1. It's the integral of the probability over all space. So each of these integrals is 1 if the wave function is normalized. We assume that the wave function is normalized. If we assume that the state vector is normalized, this whole thing is just 1/4. And we have proved now the uncertainty principle from the triangle inequality that delta x squared times delta p squared is bigger than 1/4. The 1/4, I remind you, came from 2 factors like this. Or if we wish to just, we can just write this as, we can take the square root of both sides. Delta x, delta p is bigger than 1/2. Now, what about units? X and p are not inverse to each other. So the product of an x and a p can't be a pure number. What is inverse to an x is a p over h bar. So really, this is delta p over h bar. If I put back the units, or basically delta x, delta p is bigger than 1/2 h bar. Right. This is the theorem that asserts the uncertainty principle, that the uncertainty in position times the uncertainty in momentum is bigger than h bar. Now, this would be true for any direction of space. Pick any direction of space, or any particle, any coordinate, any generalized coordinate in mechanics, its uncertainty times the uncertainty in the corresponding conjugate momentum is bigger than h bar. So that's bigger than h bar over 2, as a matter of fact. Any questions about about this particular version of the uncertainty principle? Yeah.
The integration method has another term that I guess integrates to zero, right? Because it's
Which term?
well, f times the derivative of g is the integral of f times g minus the derivative, the
Yeah.
integral of the opposite derivative.
Let's call it f prime g plus g prime x. Right. Now, if you integrate this equation, if you integrate this equation, it says the integral of f prime g plus the integral of g prime x is equal to the integral of d by dx of fg. But the integral of a derivative is just the difference between the integrand at the two endpoints of integration. So this is fg between the two endpoints, infinity and minus infinity. The symbol stands for fg evaluated at infinity minus fg evaluated at the other end of integration. And what I'm assuming is that, that psi goes to 0 at infinity, which it would have to do if it's normalized. If its integral is finite, if the probability distribution is normalized, it means that the wave function has to go to 0. So this is 0. And this is just a rule that you can interchange where you put the derivative at the cost of a sign. Right. Yeah. Okay, any other question about the uncertainty principle? Yeah.
You keep saying greater than, but we'll put this greater than or equal to. Is it a small point or?
No. No, it's not a small point. When you prove that something is bigger than something else, you can then ask the question, can it ever be equal to that something else? And the answer may, we may have proved an inequality which was not the tightest inequality we could have proved. Could have been that somebody could come along smarter and proved a tighter inequality, that it's got to be bigger than something else, a stronger inequality. In this case, it's not true. You can find wave functions for which delta x, delta p is equal to h bar over 2. So they're called minimal uncertainty wave packets. So it's not a trivial point.
This doesn't apply to time and energy.
Well, yeah, it does, but the circumstances under which you use it are less clear, and I don't really have time to explain now. We may, at some point in these courses, we will probably want to think about it. But do remember that the time dependence of a wave function, psi of t as a function of time, is a sum over the eigenvectors of the energy. Let's call it a sum over all the energy eigenvectors of e to the minus I et, that's time, times the energy eigenvector times a function. Let's call it phi of e. So the relationship between the wave function as a function of time and the wave function as a function of energy is, once again, you sum up things in energy with phases like this to get things as a function of time. That's the Fourier transform relationship. So it's, but exactly how you use it is, I'll give you an example of how you use it. If you had some wave function moving past you, it's moving past you, and you ask, how long does it take for the wave function to actually pass you? And this could be a light beam, incidentally. But how long does it take for the wave function to move past you? In other words, what's the uncertainty in the time at which the wave function might have been maximum? How long does it take the maximum to get past you? That you can call delta t. Uncertainty in time that the wave function arrived right at your nose. It's related to the uncertainty in the energy of the wave function. The bigger the uncertainty in the energy, well, let's say it the other way. The smaller the uncertainty in the energy, the bigger the uncertainty in when that wave packet will pass you, for example. That's an example of the energy-time uncertainty relation. So any pair of things which are related by Fourier expansion, and this is a Fourier expansion. It's writing psi of t as a sum or an integral over oscillations. Any two things which are related in that fashion will have a uncertainty principle. There are lots of other conjugate pairs like this. The angle of, supposing you have a rigid body rotating about a point with an angle theta characterizing its position, then the angle theta and the angular momentum have exactly the same kind of relationship. Uncertainty in angle times uncertainty in angular momentum is also h bar, I think it's h bar over 2 also. So very similar kinds of things. Okay. Any other questions? Okay. Let's turn to the Schrodinger equation. The Schrodinger equation is the equation for the way a wave function changes with time. It also governs the way expectation values, if you know how the wave function changes with time, then you can try to deduce how expectation values of observables change with time. One of the things we would like to do is to see the relationship between the motion of wave packets governed by the Schrodinger equation and their classical counterparts, namely the motion of systems. Systems in this case being a particle. We would like to see that as long as the wave packet is narrow and not too crazily spread out and not, if it's a nice bell-shaped curve, and stays a bell-shaped curve for some length of time, that the wave function or the center of the wave function moves in a way which is familiar from classical mechanics. We need to be able to do that to make any relationship between the classical and the quantum mechanical things that we've been talking about. Okay, now we talked about this. Let's first write down the general Schrodinger equation. I'm going to take you back a couple of lectures now. Take you back a couple of lectures and go through the derivation of how a wave packet moves. Okay. The answer is the wave packet moves so that its center satisfies the classical equations of motion. I'm not going to do that in a new way. I'm going to go right back to the old way that we've already talked about. And to do that, we first of all, in order to know how the wave function changes, we need to know the Hamiltonian. And let's just remind ourselves how it works. The way state vectors change with time, I d psi dt, is governed by the Hamiltonian acting on psi. Okay. If we were to take for our Hamiltonian p squared over 2m, that's the Hamiltonian for a classical particle. Why we should take it for a quantum mechanical particle is not obvious. And what might we add to that to put the particle in a force field? We might add a potential energy function. Potential energy function might be plus v of x. Okay, so that would be the classical Hamiltonian for a particle moving in a potential energy function v of x. And we can take that, we can lift that right from classical mechanics and think of it as a quantum mechanical Hamiltonian, and then check afterwards, is the wave packet really moving the way classical mechanics would say that the classical particle moves? Okay. All right, so let's try that. We will just work, in a little while, we'll just work with this abstract equation here, but let's just see what it says. H on psi, H on psi. Instead of working with abstract ket vectors, we can work with wave functions. And what this equation would say would be I d psi of x by dt is equal, now, p squared, what is p? P is minus I d by dx. P squared is minus d by dx squared, or d second by dx squared. There's a 1 over 2m minus 1 over 2m times psi. But what is v of x? Is v of x an operator? Yes, v of x is an operator. By definition, this is a definition now. I told you what the operator x does. The operator x, when it multiplies a wave function, just multiplies it by x. The corresponding thing for a general v of x is the meaning of the operator v of x is that it multiplies the wave function by v of x. We didn't talk about that much. We didn't talk about functions of x. But functions of x are just defined in the obvious way, as thought of as operators. They operate on wave functions just to multiply by v of x.
Is that because v of x is a function of position?
Yeah. Yeah. Functions of operators, yes. V of x is a function of position. X multiplies psi of x, v of x also multiplies. And you can take this as definition. When you make a definition, of course, you're later going to want to prove that it was a useful definition. You don't just make definitions. You make definitions and then show that they either are valuable because they're easy to work with, or they're valuable because they relate things to previous things you already knew. What we're going to want to show is that with this definition of how v of x acts, that the Schrodinger equation will, in fact, make particles move according to classical orbits, or at least make wave packets, insofar as they don't spread too much, move according to the classical equations of motion. All right, so that's one term, d sec 1 over 2m, second derivative of psi. And the other term is just plus v of x times psi of x. When v of x acts on psi of x, it just multiplies it. And this becomes the Schrodinger equation. This is the Schrodinger equation for how the wave function changes with time. It's also depending on time. Let's at the same time write, you know what I want to do with this? I'm going to be interested in d psi by dt. So I think I'll multiply away this I. What do? We multiply, if we want to get rid of an I, we multiply it by a minus I, right? Minus I times I is 1. So multiply by minus I, that'll get rid of this minus sign and put an I here and put a minus I here. That's psi dot, if you like. The left-hand side is psi dot. Let's also write down d psi star of x and t with respect to t. It's not a new equation. It's just a complex conjugate of this one. And that one will be minus I over 2m d second psi star by dx squared plus I v of x psi of x. Hmm?
Yeah.
I think I got it right.
T at the end.
Hmm? Did I make a mistake?
Psi star.
Hey, everybody's talking at once and I can't hear. Oh, yeah, good. Psi star, good. Right, those are the Schrodinger equations. They're equivalent to each other. I just wrote them both because I'm going to need them both. Okay. Now what do we want to do? We want to see how various expectation values change with time. If we identify the expectation value with more or less the center of the wave packet, if the wave packet looks like this, the center of the wave packet will be close to the expectation value. And so let's identify the center of the wave packet with the expectation value and ask how expectation values change with time. Let's see if we can work it out. All right, so let's start with x. Let's see if we can calculate d by dt of the expectation value of x. And that, of course, is d by dt of the integral psi star of x, x squared, no, just x, psi of x.
When you wrote down the d over dx at the start, you said dt?
dt, d by dt. In other words, the velocity of the center of the wave packet. That's all this is. It's the velocity of the center of the wave packet. Why does it change? It changes because psi changes. How do we know how psi changes? We know how psi changes because we know the Schrodinger equation. So this is going to be a little exercise, a little bit too tedious for my taste to do on the blackboard. It's not very tedious, but still, I may cut little pieces, take some shortcuts, but I'll tell you when I do. Okay, so this is what we want to calculate. And this, of course, x is just x. It's not dependent on time. But psi star and psi are dependent on time. So when I differentiate, I get a term from each one of these. And this will give me integral the psi star of, well, let's just write the d by dt psi star x psi plus integral psi star x psi dot. All right, one term coming from differentiating with respect to time psi star, another one from differentiating psi. Each one has x in there. And now, of course, this is just psi star dot. All right, first thing is we don't really have to calculate both of these. These are complex conjugates of each other. We have psi star dot here, we have psi dot here. We have psi here, psi star here, and x is real. So in fact, all we have to do is calculate one of them and add its complex conjugate. That's all we have to do. Or equivalently, just take twice the real part. Adding something to its complex conjugate, the imaginary parts cancel, and it's just twice the real part. All right, so we can use that. I'm not sure we'll need it, but let's say it's twice the real part of this. Twice this, and keep in mind that we throw away anything that's imaginary. We throw away anything that's imaginary because we add the complex conjugate, and that will throw it away. Okay, so now let's plug in d psi star by dt over here. And that gives us minus I over 2m d second psi, well, let's see, what are we doing? It's plus, I'm sorry. It's plus I, it's the upper equation there, d second psi by dx squared I think it's minus I v of x psi. Okay. Now, the first thing we can see immediately is that the term with v of x is pure imaginary. There's psi star, there's x, there's psi. Psi star psi is certainly real. X is real. V of x, the potential energy, is real. And there's an I there. So the first thing to conclude is that the V of x doesn't contribute at all. It doesn't contribute at all because when you add the complex conjugate, it will cancel. So in this equation, we can throw this away over here. Psi star x, V of x psi, that's real. With the imaginary part, it cancels. So we can throw this away. Okay. Next, what's the next step? Integrate by parts. That's always the next step. It's always the next step is integrate by parts. We have here a derivative. It's a second derivative, but a second derivative is also a first derivative. Let's write it that way. It's d by dx of d psi by dx. Incidentally, partial derivatives have no, well, yeah, they do mean something. They mean derivatives with respect to x without changing time. Yeah, okay. All right, so that's our equation. And now I want to integrate by parts, which means I want this d by dx over here to shift to the other factor. I want to shift it to the other factor, and I'm going to get two terms. Let's look at what the two terms are. The first term, the d by dx will just hit x. What does that give? What is d by dx of x? 1. So that will give me twice integral psi star. The x will disappear when d by dx hits it. And there is d psi by dx, right? d psi by dx. This derivative got shifted to here. There's an I think, over 2m, right? There's an I that I left out over 2m. Oh, what else did I leave out? Integration by parts. Minus. That's one term. Now, again, you might think this is dangerous I here. We should throw it away because it's imaginary, but it's not imaginary. It's real. We'll see that in a moment. Okay, well, in fact, we'll see exactly what it is in a moment. But let's do the other term. The other term has an I over 2m. I over 2m. There'll be an x. The x does not get differentiated now. X. And then there is the psi star of x. Now the derivative hits the psi star, and we get derivative of psi star times derivative of psi. Okay, this derivative now hits the psi star. There's an I here, an explicit I, and this is to be integrated over x. It's still underneath the integration here. How about this? What's the reality property of this? Is this real or imaginary? There's probably a minus. Yeah, there is a minus. Okay. But it's imaginary. This is the complex conjugate of this, and x is real. So this integral here, the integral here is perfectly real. It gets multiplied by minus I, and the whole thing is imaginary. It will get eaten when you add the complex conjugate. So the only thing that's left is this. I over 2m with a minus sign times psi star d psi by dx. Now I'm going to tell you exactly what this is. What is minus I d by dx? It's P, right? It's P. Minus I d by dx is P. So what this is it's the expectation value of P divided by M, P over M. Just look at it. D by I, minus I, d by dx on psi, that's the same as P on psi. Multiplied by psi star, that's the bra vector. Integrate over x, that's just taking the inner product. All right. In fact, it's real. In fact, it is really real. It looks imaginary because of this, but if you go and study it carefully, you find that it's real, and what it is the expectation value of the momentum divided by m. So now we've proved an interesting theorem. We've proved that dx by dt is equal to P over m. We've seen this before. This is the classical relation between velocity and momentum. Mass times velocity is momentum. Now what we found is that this is going to be a feature of the motion of a wave packet. If we have a wave packet that moves in a nice way so that it holds itself together, which it may or may not do, but if it does, if we're in a regime of parameters where the wave packet moves like a nice wave packet, then we will find that the expectation value of its momentum, defined in this way, will be related to the expectation value of the velocity of the wave packet through the standard classical mechanical equations. Okay, that's half of mechanics. What's the other half of mechanics? We found that oops, I just gave it away. dx by dt is P over m. What's the other half? dP by dt. That's Newton's law. Time derivative of momentum is called force. So let's see if we can do the same thing with momentum.
Question?
Yeah.
In your summary, when you said that if everything is kind of grouped nicely, it would behave that way. We didn't have a nicely grouped assumption in our derivation, did we? Or is it just that that's going to it's going to look classical if it's nicely grouped?
Right. Yeah. There was no assumption here. There will be, as we'll see, a certain assumption in the other equation. No assumption here of that type. Okay. If the wave packet is really crazy, it might not mean anything very sensible, but still, that was a nothing I did up till now depended on any approximate notion of how the wave packet moves. Okay, we got this. Let's see if we can get the other half. Now, I don't guarantee to be able to get through it without all sorts of errors of i's and minuses, but let's try this one. All right. P, the average of P is gotten by acting with P on psi, and that's minus I. It'll give us a minus I, which I'll put over here, but then d by dx. d psi by dx. We could put the derivative over here by an integration by parts and a sign change, but we'll leave it over here.
Are we looking for d dx?
Hmm?
Are we looking for d dx of p? Or is it d on the very left-hand side? Should that be an x on the bottom?
Where?
d by d.
No, no.
Yeah, it should be
No, no. We want the time derivative of the momentum. What do we want to see? We want to see that the time derivative of the momentum is governed. Let's write Newton's equation. P dot is equal to force. That's it. What is force in terms of the things I've written on the blackboard? Minus dv by dx. So this is what we're going to want to show, minus dv by dx. But we'll show it in the form that d by dt of the expectation value of the momentum is minus the expectation value of dv by dx. dv by dx is also a function of x. If v is a function of x, dv by dx is a function of x. It's called a force. So what this says is the average rate of change of momentum is the average of the force. The force, the dv by dx is minus f. Okay, so that's what we want to show. We want to show that dp by dt is dv dx. That's our goal. Okay, and how are we going to show it? Once again, we're going to show it by using the Schrodinger equation to tell us how things change with time. Okay, so let's see now. This may get a little bit unpleasant. I'm not sure. Right. What I'm debating. All right, let's start working it out. And at some point, I may say, well, I know this goes away and this doesn't go away, but we'll see how it goes. Okay, so first of all, this gives us integral psi star dot times d psi by dx minus I. And then there's another term. Where did that come from? That came from differentiating psi star with respect to time. Then there's going to be another term where d by dt will hit psi. Okay, so what will that be? That will be, again, minus I integral psi star. Now, the order of differentiation doesn't matter, so this can be written as d by dx of psi dot. I'm just wondering, at one point, I'm going to regret not having done an integration by parts. But it won't matter, because if I do the integration by parts, I will regret it. So I might as well just go ahead. Is there an extra I? No, I don't think so. I don't think so. No, I think it's right. Okay. Oh, you know what? I think it will be convenient to integrate this one by parts. If I integrate this one by parts, I will get a plus I here and a d psi star by dx here. Now, the reason it's convenient is because the thing in here is the complex conjugate of the thing here. Okay? Psi dot star, well, that's the complex conjugate of psi dot. D psi by dx, that's the complex conjugate of psi star. But notice it's I times the difference. What do I get when I take I times the difference of two complex conjugates? You get a real thing again. All right? So, I think it's just the real part of this. Well, let's just keep going. Let's just keep going. We can erase this and remember in the end that the answer has to be twice the real part of this. Twice the real part of this. And we don't have to keep track of both of them. Okay, now, what do? We plug in the Schrodinger equation and pray like mad that it all goes well. Okay, so psi dot is equal to I over 2m d second psi by dx squared minus I v of x psi. This I cancels this I and gives a minus sign. So this I, well, there's an I here. This will make minus. And the I over here times the I over here, I think will make plus. Plus. Okay, we have a somewhat unpleasant thing here. How unpleasant is it? Let's see. Not too bad. This piece, I believe, is pure imaginary. It is. It is. It is. This is pure imaginary over here. The way you see it is, again, integrate by parts. Just this piece here. If I integrate this piece by parts, we'll get a derivative, we'll get a term with a single derivative of psi and a second derivative of psi star. Okay? What we'll discover is basically the difference between a thing and its complex conjugate. There'll be a minus sign. Okay, let's just see it. Yeah, let's just do it. If I differentiate, or sorry, integrate by parts, that'll bring the derivative over to here. It's pure imaginary. I know that it is. Whenever you have a quantity complex conjugated times the derivative of the unconjugated thing and you integrate it, it's always pure imaginary. We've used that trick before. I'll just tell you right now, this piece is pure imaginary. It's not going to be of any significance. The significant piece is integral d psi star by dx v of x psi. That's all that's left after we take into account the little intricate details of complex conjugation, v of x.
Now we double it?
Hmm?
Now we double it?
I can't remember whether we doubled it or not yet. I think we double it. I think we double it. Yeah, we double it. We have to double this. Okay. Yes, we have to double it. Or add it to its complex conjugate, I would say, right? We have to add it to its complex conjugate, I think. In fact, let's do that right now. Let's add it to its complex conjugate plus the integral of psi star v of x d psi by dx. All right, I've taken this and complex conjugated it. I've taken this and complex conjugated it, and v is real. Okay, now we're almost there. We have d psi star of x dx times psi. Let's pull out the v of x. Let's pull it way out here, v of x. V of x times this. Now what is d psi, what is this thing here? Psi times d psi star of x plus psi star times d psi by dx. It's the derivative of psi star psi with respect to x. This is derivative of psi star times psi plus psi star times the derivative of psi. That is nothing but the derivative with respect to x of psi star psi. So let's put that in. And the next step integrate by parts. All right? Integrate by parts. That'll take the derivative over to here, and it will give me minus the integral of psi star psi times dv of x. Or if I put the psi over here on the right, and what is this thing? The integral of psi star psi times dv dx, that's the expectation value of dv dx. This whole thing is the x minus the expectation value of dv dx. In other words, it's exactly this. So what we found after a slight bit of painful integration by parts and a little bit of algebra and throwing away some things which I told you were pure imaginary, which they were, we find that dp by dt is exactly equal to minus dv by dx, but in the sense of expectation values. In the sense of the expectation value. All right. Now, why do I say, this also is exact. I didn't do anything illegal here. I didn't do any approximation. I'll tell you where the use or where it may be important that the wave packet have a nice shape. The expectation value of dv by dx is not the same as v or d. Let's just take v. Let's just take v. The expectation value of v of x. No, let's call it f of x, force. The expectation value of f of x, it's really annoying, which is, after all, minus dv by dx. The expectation value of a function of x is not the same thing as the function of the expectation value of x. This represents the expectation value of x, the center of the wave packet, and this is a function of the center of the wave packet. It is not the same thing as the thing we calculated in general. This is the expectation value of f of x. Let me give you an example where they're very, very different, where they could be extremely different. Suppose, for example, that f were equal to x squared. Supposing the force happened to be x squared, and supposing the wave packet consisted of a pair of bumps. Let's see, is that what I want? I think that's what I want. Yes, that is exactly what I want. Centered about 0. What is the expectation value of x? What's f of the expectation value of x? 0, right? On the other hand, what is the expectation value of x squared? Certainly not 0. This one has an x squared that's equal to the x squared of this, right? It's certainly not 0. So when wave packets are not nice single bumps, which are mainly characterized by their centers like this, then in general, you could not write that the time rate of change of the momentum is equal to the force evaluated at the expectation value of x. It's only if the wave functions are nice and so that concentrated over a fairly narrow range. If they're concentrated over a reasonably narrow range, then the expectation value of f of x is the same as as f of the expectation value of x. This is where we have cheated a little bit in saying this looks like the classical equation of motion. That depends on the wave packet being nice and coherent and well localized. What are the circumstances under which a wave function will remain nicely localized? Well, I'll tell you what the circumstances are. the circumstances are that the particle is heavy. If the particle is heavy and takes two things, the particle being fairly heavy and the potential energy not having too many spikes, not having spikes in it or something like that. Spikes, when the wave function hits spikes, it tends to break up. For example, if you have some sort of wave function coming in, a nice wave packet coming in, moving to the right, and it hits a point structure here, what will it do? It will spread out all over the place like that. The wave function will disintegrate all over the place. If, on the other hand, it hits a very smooth potential of some sort, then it will go through the smooth potential, moving more or less according to the classical equations of motion. So, we don't expect quantum mechanics to reproduce classical mechanics in every possible circumstance. We expect it to reproduce quantum mechanics in circumstances where it should, where particles are heavy and where potentials are nice and smooth and don't cause the wave function to break up into little pieces or disintegrate or scatter all over the place. Okay. Let's see if there are any other odds and ends that I wanted to.
Harmonic oscillator?
No, not tonight. That's we don't have time for it.
Question about what you were just describing. What sort of physical situations would correspond to, quote, bad potentials that break up the wave function?
Well, okay. The situation which is bad tends to be when the potential has structures and features in it which, let's say, have some size associated with them, some structure which we can call delta x, some size associated with the structure here, and where delta x is significantly smaller than the uncertainty in position of the particle. If the structures, what do we want to call them? Features, sharp features of the wave function take place on a scale which is much smaller than the size of the incoming wave packet, then it will break up the wave function into a lot of little pieces. Each one will scatter. They'll scatter off in different different directions. Did I write this right? Yeah, that's right. Okay, let's.
Isn't it the case then, it's in those cases where, in some sense, classical mechanics itself is breaking down. Is that right?
Where, yes.
In other words,
Yes.
you shouldn't expect it to replicate.
No, you shouldn't
classical
expect it. No,
mechanics
of
because
course.
it's-
Of course, right. When there are basically when the features in the potential are shorter than the wavelength of the particle, it'll break it up into right. Now, if you were to take a bowling ball and you were to ask what is delta x, well, let's see. Typically, it's true that typically delta p times delta x, the rule is that it's bigger than h bar, but in many reasonable cases it's of order h bar. Now, p, that's about as concentrated as you can get it, but for an ordinary macroscopic object, the uncertainty principle is pretty well saturated. Delta p times delta x is more or less about equal to h bar. Why that's so is a very complicated question, but very complicated. Now, what is delta p? Delta p is the mass times the delta velocity. Okay? So the uncertainty in velocity times the uncertainty in position is h bar over m. Now, if I put a bowling ball down on the ground you know very well that the uncertainty in its velocity is not very big. The uncertainty in its velocity is, in particular, as it gets heavier and heavier, you might expect the uncertainty in the velocity gets smaller and smaller. And in any case, there's an m down here. And so whatever delta v is, as m gets smaller and smaller, delta x will get bigger and bigger, right? Delta x will get bigger and bigger. Right. And in particular, it will tend to get bigger than the features in the potential. So in the highly quantum mechanical limit, where mass is very small and delta x tends to be big, the wave function will move under the influence of a ragged potential which it sees as being much sharper and much more featured than the wave function itself. That's when it breaks up. On the other hand, as m gets very large, delta x gets small. Delta x will tend to get small as m gets very large. And so for a large bowling ball, the wave packet might be very, very concentrated. And when it moves through here, it moves through like a tiny wave function. And the tiny wave function thinks that these features are very, very broad. Moving through broad, smooth features doesn't disrupt the wave function and break it up into pieces. So large mass and smooth potentials is the limit of classical physics. Light mass and abrupt potentials is more quantum mechanical. Yeah.
Just to get a feel for what you mean by large and small, if you,
No.
is an electron large enough to behave classically as it's flying?
It's an interplay between the shape of the potential and the mass. If you take a very, very smooth potential of the kind that you might make, let's say, with a couple of capacitor plates. Capacitor plates separated by a meter. Well, we don't have to take a meter, a centimeter. With a smooth electric field between them, then the electron will move through it as a nice, coherent, almost classical particle. On the other hand, if you take the potential associated with the core of the atom, the nucleus, that has a sharp feature in it, and that sharp feature will, if an electron wave comes and hits it, will scatter it all over the place. So it's an interplay between the mass and the sharpness of the potential.
So can you do that experiment with a nucleus and an electron and show that it actually does behave?
Absolutely. Yep.
And isn't that what led?
Let's not do, of course you can do it with an electron. No problem with an electron, very easy. The classic experiment was done in 1911. It wasn't done with electrons. It was done with alpha particles. Alpha particles come in and hit a gold nucleus. A gold nucleus is a small thing, and the result was that the gold nucleus, when the alpha particle comes in, the wave, quantum mechanical wave of alpha particles comes in, hits that tiny gold nucleus, and it gets scattered in all directions. That's why Rutherford was a bit surprised to see his alpha particles get scattered right back at him. And what did it tell him? It told him that the nucleus was very small. Right.
Well, he didn't understand quantum mechanics.
I didn't. Right. He just thought he had a beam of alpha particles, some of which hit the center, some of which went through here. Right. But in fact, what he really had was a wave. And the wave came in, hit the tiny gold nucleus and got scattered all over the place. And with electrons, yeah, sure, it's very easy. That's what happens in accelerators when electrons hit small targets. They just scatter. Oh, photons do also. Photons do also. Electromagnetic waves, if they hit structured objects with a structure size smaller than the wavelength, they get scattered all over the place. If they hit very smooth things, they tend to propagate according to the geometric optics. For example, if you have a piece of material with a position-varying index of refraction, if that index of refraction is varying very smoothly and very slowly over the wavelength of the photon, then geometric optics is a good approximation. If, on the other hand, you have a diffraction grating of distance comparable or smaller to the wavelength of the radiation, the diffraction grating will spread it out all over the place. Okay, so it's not just electrons, photons, anything. Okay, if there are no other questions, I'm going to go home and find out if my son had his baby yet. Okay.
For more, please visit us at stanford.edu.